Hello and welcome to A-Level Physics. I think you've chosen a really good A-Level to explore. It's an incredibly interesting subject dealing with the nature of the world that exists around us. It's also a subject that opens a lot of doors for your future career, particularly in fields like engineering and other sciences, as well as in those subjects that require the sort of skills you'll develop in physics, which are good numeracy and problem solving skills. So in this short course, this short presentation, what I'm going to talk about is what's involved in the course, what you can expect from us as your teachers, what we'll be expecting from you, so you get a better idea of what you're getting into once you start A-Level Physics. I've listed what the contents are for AQA's curriculum for A-Level Physics. So you see that there are 8 core topics that are explored by everybody who does A-Level Physics, and then there is an option topic, and there's a variety of options that can be chosen. At Holcombe we chose astrophysics. So one of your teachers, Mr. Milne, is an expert in this area. He's an astrophysicist, which is one reason why I've chosen it. It's an area that I think is of interest to most people dealing with space. And thirdly, it's an area that, in terms of your exam, tends to be quite accessible in terms of the sort of questions that you might be asked in your exam. So the course divides into 2 years. In the first year, you'll be looking at the first 5 topics. Topic 1 is one that you really explore over both years. It's to do with how you work in practicals, but we will be learning this in your year 12 right from the very start. And then the 4 main content are particles, so the particle physics, waves, mechanics, and electricity. Then in year 13, that builds on top of the year 12 material. So there are further mechanics. We then have an introduction to the concept of fields, and then nuclear physics. So it's sort of the year 13 topics really build on top of the year 12 topics. Now, just for completeness, I've put in here the AS paper. So this is normally what would be done at the end of year 12. And these are papers that, as you can see, it tests your knowledge on sections 1 to 5. So you will not be sitting an external AS paper at the end of year 12, but you will sit an internal exam that will be in format very similar to AS. So it will test you on everything from year 12, sections 1 to 5, consisting of 2 papers. Your A-Level exams at the end of year 13 are based on testing you on everything. So paper 1 tests topics 1 to 5 and part of topic 6, which is the further mechanics topic. Paper 2 tests on all the rest of the content, so that's the rest of topic 6 and then 7 and 8. And then in paper 3 we have the test on the option subject, which for us is the astrophysics. And there are a series of practical questions based on the practical content and skills that you've developed over the 2 years. There are 3 of these papers. Each paper is 2 hours long. Now, the usual requirement we have for entry into A-Level Physics is as shown on the screen. We have grade 7 or above in physics, or a grade 7/7 in combined science, and a grade 7 in mathematics. Most people who take A-Level Physics also take A-Level Mathematics. The 2 subjects are very closely linked. The language of physics is mathematics, and it's very difficult to access the A-Level Physics topic if you're not confident and competent with mathematics. So normally, although it's not required, we recommend to people that they take A-Level Maths as well as A-Level Physics, but it isn't required. What is required is that you have at least a grade 7 at GCSE Maths. Now, both myself and Mr. Milne we're really keen on physics. We find it an incredibly interesting subject based as it is on exploring how the entire universe works. And it's often a subject that's most interesting and most fun for people who like problem solving, who like being able to work out um, how things work or how to solve problems. However, we're moving into A level, and it's very important to realize that A level is a significant step up from GCSE. A lot of GCSE, particularly in something like physics, you can get by learning a set of equations, learning how to answer some questions in a typical way. But A level is much different. It's much more challenging to study. You need to know topics in a lot more detail. This is why A level involves only 3 or 4 subjects compared to perhaps 9 or 10 at GCSE. So the thing to realize is that if you come into A level and you were to work on the subject at the same level as you worked at that subject at GCSE, and you had a really good result at GCSE, you were a grade 8 or grade 9 at GCSE, that will translate into around about a C or a D at A level. So this is the idea that I want you to understand about A level, and this applies to all levels, not all A levels, not just physics, that it involves a significant increase in the amount of work that you do and the amount of attention that you put to this place on the subject because of the amount of detail that you need to be able to deal with. So you need to be very good at organizing yourself, making sure that you have easily all your notes, that you know where things are, that you know where all your homeworks are, that you're punctual, that you meet all the deadlines. But the fourth thing written on this slide is really something that is perhaps the most difficult to become used to at A level. You need to become much more independent with your work. So as well as coming to lessons and doing the homeworks, you need to be spending time doing independent work on the subject. So the way I'd like to think about it is that you need to think of your A levels like a job. So a job typically has 40 hours a week. So if you have, let's say, you have 3 A levels, then you should be spending something around about 12-13 hours a week on each of the subjects. So that means that as well as spending time in your lessons and doing your homework, you need to be trying to read around the subject later on when you're getting ready for exams, doing lots of exam practice. And it's really the key difference between those students who are the AA star students and the students who are bright but perhaps are still at the C or maybe even B level. It's this amount of dedication to the subject outside of your lessons and homework that makes the difference. We also say it's very important that you realize that both of us as teachers, we are here to help you through this course to make sure that you do as well as possible. So if as soon as any difficulty or problem arises, you need to speak to us. The earlier we get to address any issues that arise, the better. We will be offering support sessions at some point during the 2 years, and you should, if you require it, make effort to attend these support sessions, and in particular, listen carefully to the advice that you're getting and try to follow it. Some more housekeeping type of expectations. These are the sort of things that we expect you to have. We expect you to have your homeworks, your notes, exam papers that you've worked on, worksheets that you've completed. We expect you to have that organized in some way. We would suggest having some sort of large lever arch file, and then you can use dividers to separate it into the different sections so that you have your work in one place. If you want to organize it in a different way, that's fine, but you need to make sure, because you will have a lot of work, you need to make sure that you have some system that allows you to easily access anything that you require. Obviously, in lessons, when you're in your study period, at home when you're working, you need to make sure you have all the equipment you need, pens, pencils. rubber sharpener. Ruler and protractor are things that are required as well. And calculator. Now for a calculator at A level, you are allowed to use a graphic calculator. If you're doing mathematics, they will also require that you use a graphic calculator. And becoming skilled at using a graphics calculator is really incredibly useful, as it makes the learning process much, much easier. We would recommend that you have at least a revision guide as a textbook. We don't recommend that you buy other textbooks, but you are welcome to, and we can advise you on which ones to go for. But you should at least have a revision guide. And you will be doing a set of required practicals, and we would recommend that you purchase a pre-printed required practical lab book which you write in, as it's helpful for organization of your notes for the required practical, and it helps when you come to demonstrate your competencies in required practicals, and we'll look at this a little bit later. So that's what we expect from you. Now you can see what you can expect from us. So in terms of the lessons, you will have a series of lessons over the 2 years, and we will cover all aspects of the specification. We have both taught A-level physics for a number of years, and we will ensure that there are no aspects of the course that you haven't been taught, and we will give you opportunities to carry out the experiments that will help you to reinforce and help you to understand the application of what you're learning. We will also provide everything that you need to achieve what's called your practical endorsement, with a minimum of these 12 required practical experiments. You have 2 specialist physics teachers. So Mr. Milne, as I said before, is a specialist in astrophysics, so he is more a pure physicist. For myself, Dr. McGovern, I am an engineer, so my specialism in physics is more on the engineering side. So between the two of us, we tend to cover quite a wide range of the physics course, and as I said, we're both experienced A-level physics teachers. We will also run additional support sessions after school, and most days you'll find that we are normally at school after the school day has finished, and you'll always be able to find some time where we will be able to support any questions that you have. So far what I've talked about is this introduction to A-level physics, what's involved and what you might expect once you start the course, both for yourself and from us. I'm going to, for the rest of this presentation, talk a little bit about the practical work and give an example of one area that you will need to become competent in, and there's some work for you to practice these skills that we're going to talk about. But one thing we would recommend during the summer holidays is that you look at the homework pack that we put together. So it involves a number of tasks that will help you be really ready to go at the start of the course in September, and Mr. Milne will go through these in more detail in the second of these presentations. The major difference with the courses from the A-level courses in the past is that, as well as the course being linear, in the past it was more modular, where you did exams on particular parts and then moved on to other parts. The exams at the end are on everything, and they also include questions that will test your knowledge and skills in doing practicals. So there is no coursework involved in A-level physics. There is no work that needs to be handed in as a non-exam assessed piece of work. However, there is an endorsement on your A-level certificates called a practical endorsement if you pass the required practical part of the course. So, and a lot of universities, they expect that you have passed this part of the course. It's based on a minimum of 12 required practicals. do you pass this required practical part of the course? Well, this is something that we as teachers, we will be closely tracking your work during the 2 years to make sure that you know where you're at, how close you are, and if you're on track to passing this part of the course. Essentially what you need to do is you need to show that you're safe and confident in the lab. You don't need to do practicals perfectly from the start. That's not expected. That's part of the learning process that you're going through during the 2 years. But the idea is that at the end of the 2 years of this A-level physics course, we as teachers, we can sign a document to say that, yes, if you go into a lab in a university and you're given some work to do, you would be safe and you would be capable of getting valid results. So what you need to do is you need to show how you develop your skills over the 2 years against a set of practical criteria, and these are in 5 areas. So you don't need to remember these in detail now. This is something you become very familiar with over the course of 2 years, but these are the 5 areas that we will be looking at. Area 1 is simply that you're able to follow the written procedures correctly. Area 2 is where you apply investigative approaches and methods. So this is where you're able to adjust what you're doing to make your results more accurate or to deal with any issues that come up, that you're able to properly identify any control variables, that you're able to carry out the experiment and use the equipment with minimal help or assistance from your teachers. Then 3 is obviously a very important one, and 3 is all about safety. Safety is about you showing that you're able to, before the experiment, identify hazards, assess any risks involved, and make any safety adjustments that you need to make to stay safe. And then the second one is more practically that you're able to use the equipment safely and you know how to use any safety equipment like goggles properly. Then the 4th criteria is that you're able to make and record observations correctly. And the 5th one is where you're able to analyze the data properly, perhaps using software like Excel to carry out the analysis. You're able to then use that to report your findings properly, and you're also able to do background research to find out the necessary information from prior experiments, from articles dealing with this area, to compare what you've done to what other scientists have found, and that you're able to reference those correctly. Okay, so I'm going to give part of a lesson dealing with a couple of practical skills that you'll be developing over the course of 2 years. The first thing I want to look at is our ability to understand the difference between things being accurate and things being precise. So I've given 3 examples in the slide here. Now, if you turn your attention to the first one, what it says is in 1650, Ussher, this was a Bishop Ussher, he studied the Bible. He was a great theologian of his time, and he studied the Bible, and he went through each of the main characters that were mentioned in the Bible to work out when the date of creation was. And he came up with a date that the earth was created on the 23rd of October 4004 BC. Now, this is an incredibly precise answer. This is incredibly precise. This is equivalent to having lots of decimal places in your answer. However, it is incredibly hilariously wrong. So he said the earth was created in 4000 BC, when we now know the earth is around about 4 billion years old. So that's what's called a significant error in physics. Then, not that long after that, there was a Danish astronomer in 1676, and he measured the speed of light. Now this is a really tricky problem if you think about it, because light moves so quickly. So he was able to come up with an experiment that allowed him to make an estimation of the speed of light. And he came up with an answer of 210,000 kilometers per hour. So if you compare that to what the actual answer is, that's an error of around about 30%. You'll notice it's not very precise, so we don't have lots of decimal places. We've got 210,000, so we've got a load of zeros here, so this is not a precise answer. However, it's quite an accurate answer, especially given the time period and the equipment that he had to work with. So this is a reasonably accurate, not very precise result, whereas the first one was completely wrong, but very precise. Then I give a third example. So in 2017, some physicists measured this property of protons called the magnetic moment, and they found it to be a value of 2.792847344462, plus or minus this number. So here we've got lots of decimal places. This is an incredibly precise number. This is a very small quantity, and this is an incredibly precise number. It's also incredibly accurate when we compare it to the predictions from theory. So this is both accurate and precise. So the first one, which is precise but not accurate, the second one, which is accurate but not precise, and the third one, which is both. And one of the most important skills that we try to develop as scientists is to get results that are both accurate, that measure what something is accurately, but also measure it precisely. I have a number of terms, key terms, that you need to become familiar with in terms of working in a lab. First one is random error. Now, a random error is an error that's introduced by quantities or variables that you can't control. So these are things that are happening because of the room that you're in, because of the nature of things. For example, if you're trying to measure something that's got a very small mass, then air currents might have an effect on that, and that's not something you can control. So random error are errors that are introduced by things that you can't control, and normally there are as many of these above the actual answer as below. So one way to deal with random error is through doing averaging. Systematic error, on the other hand, systematic error is caused typically by the equipment that you're using or something in your method. So for example, if you're using a voltmeter and the voltmeter is got what we call a zero error, so instead of starting from 0, it starts from 0.5 volts, then all your results are going to be 0.5 volts too high. So we don't deal with this through averaging, we deal with this by figuring out what's caused our systematic error and how much the systematic error is, and then removing that from our results. Now, a precise result, so in terms of precision, a precise result means there's a very small spread of our results. So our results are all grouped around the mean of these results. It might be that these results aren't actually close to the answer, the real answer. So this is like on a dartboard. If we threw lots and lots of darts and they were all very close together, but they're all in the section of the dartboard for 1 point. So they're all off on the top right of the dartboard, and they're not centered around the bullseye. An accurate answer, on the other hand, an accurate answer is an answer that's close to the actual result. So you could imagine on the dartboard again, all my arrows are all in a circle around the bullseye. They mightn't be they might be more spread apart, so they're not necessarily precise. But if I was to take an average of those that data, I would get an answer very close to the actual result. Reproducibility is one of the most important things in science. this is that whenever you do an experiment and you get a result, it is said to be reproducible if somebody else can repeat your experiment in a different place at a different time, perhaps using a different brand of equipment, and get the same result that you do. So this is one of the key elements and the reason why science has been so successful, in that the experiments are designed and tested to see if they're reproducible, and if not, then it's considered that the results aren't valid. There was a really famous case of this many years ago, in something called cold fusion, where some scientists claimed that they were able to cause nuclear fusion, which is a process that, as far as we know, requires very, very high temperatures and pressures. They suggested that they were able to do it with a process at room temperature in an ordinary chemistry lab. However, other scientists weren't able to reproduce their results, so we know that their results weren't valid. Resolution. So resolution refers to a piece of equipment, and it lets us know what's the smallest change that can happen in whatever quantity we've got that could be measured by our piece of equipment. So if you look at a typical 30 centimeter ruler, the smallest unit on the ruler is typically 1 millimeter. So the resolution is normally the smallest number on the piece of equipment. Okay. Accuracy seems to have crept in twice, so we can ignore the second time. And then uncertainty. Now, uncertainty is something that people find a little bit difficult to imagine what it means at the start, because it's not accuracy and precision. Uncertainty gives us the interval in which we think the actual value of a measurement lies. So we make a measurement of some quantity, let's say a measurement of length, and we say that it's 23 centimeters. But when we've made that measurement using a piece of equipment, what that actually means is 23 centimeters, it might have been 22.9 centimeters or 23.1 centimeters, somewhere in that region. And that's what we mean by uncertainty. It's about a single measurement or a range of measurements that we've made. It's not about the true value of whatever the quantity is. It's about our measurements of that quantity when we're doing the experiment. And we're going to look at uncertainty a little bit more. To introduce the concept of uncertainty, I'm just going to use the idea of density and measuring the density of different objects as a way for us to discuss this idea of the uncertainty in our measurements. So density is defined as the mass of the object divided by the volume of the object, how much space it takes up, and it's shown by this equation, which is rho is equal to m over v. So you can use this slide to just remind yourself how we measure the density of different types of objects. Now, I said already that uncertainty is to do with the measurements. It's what interval is our actual measurement in. So if we look at this digital thermometer here at the bottom, it says the temperature that's been measured is 38.0 degrees Celsius. Now, because it only measures to 1/10 of a degree, we have no idea what number is next after this 10th, what number we have in the hundreds. Also, we don't know if the actual number is going to be bigger than 38.0 or smaller than 38.0. It could be that the number is actually 37.99, which has then been rounded to 38.0. Or it could be that the number is 38.04, which has then been rounded down to 38.0. So when we have a piece of equipment like this, we can say that the uncertainty, it's either going to be either 1 above or 1 below. So it'll be 37.9 to 38.1 degrees Celsius. So we use the smallest number on the piece of equipment to let us know the resolution of the equipment, in other words, to let us know what the uncertainty will be. Likewise, in this picture of a ruler, what typically we think is that if I measure something, I can measure to halfway between 2 of the ticks, so in a ruler that would be a half a millimeter. But we have to remember that we could have not completely aligned correctly on the 0 side, because we need to align the 0 side and the other side. So overall, with a ruler, we say that our uncertainty, when we measure something, for example, here we might say we have 27 millimeters, and we would say that the measurement is 27 plus or minus 1 millimeter. It could be as far down as 26, it could be as far up as 28. So it's 27 plus or minus 1 millimeter. And then likewise here we have a measuring cylinder, and we measure the value using the bottom of the meniscus. So anyone who's doing A-level chemistry in particular would be very familiar with this. So here we have, well, what's our value? That's 32. 4, 5, 1, 2, 3, 4, 5. That's 33. It looks like it's 33.1. 33.1. But again, that's going to be 33.1 plus or minus 0.1. That's our measurement. Uncertainty or interval around our measurement, it can either be expressed as an absolute uncertainty or a percentage uncertainty. So to understand this, we can take a look at this example. So here I've written down an example of where we've taken the measurement of a voltage and we've measured 5.3 volts. And then we look at our voltmeter and we see that the resolution of the voltmeter is 0.1 volts. So we say that the absolute uncertainty on our measurement, so it could have been anywhere between 5.2 and 5.4. So we say that our voltage has got a voltage of 5.3 volts plus or minus 0.1 volts. We can also express this in terms of a percentage. So this is where we take this 0.1 volts and we see how much of this original 5.3 volts is this. In other words, how much of an impact is this uncertainty having on our measurement. So in this case, we would do 0.1 divided by 5.3 times 100. So that gives us an answer of percentage uncertainty at 5.3 volts plus or minus 1.9%. We can see from this that one way we can reduce, because if we're using a piece of equipment, the uncertainty is always going to be the same, in this case plus or minus 0.1 volts, but we can reduce the percentage uncertainty by measuring larger quantities. This slide, this just repeats what I've said. We've got, if we take any single reading, the absolute uncertainty, it's normally the smallest division on the measuring instrument. The percentage uncertainty is that value of the uncertainty divided by whatever the value of the measurement was times 100. However, if we take repeated readings, so instead of measuring just 5.3 volts, we repeated taking measurements of the voltage. We've got 5.1, 5.4, 5.3, etc. Then the absolute uncertainty is the range of those measurements divided by 2. So we have an example here where we've taken 7 readings, 5, 6, 5, 4, 5, 6, 4. So those are our readings. The mean of those readings is 5, and the range is 2, from 4 up to 6. So in this case, we would say our measurement is 5 plus or minus 1, and in this case, we said the readings were in millimeters, so the units are millimeters. So our measurement would be 5 plus or minus 1 millimeter. Now, one question that arises is, okay, we've taken a measurement of the voltage, and let's say we take a measurement of the current as well, and we're going to calculate the resistance. How will we know what uncertainty we have in a value of some quantity that we calculated by using a number of measurements? And to do this, we need to use the rules that are outlined at the bottom of this slide. If we're adding in quantities together, then what we do is we add the absolute uncertainties. So if I had 2 lengths, as I measured in the previous slide, one is 5 plus or minus 1 millimeter and the other is 6 plus or minus 1 millimeter, and I want to know what is going to be the overall uncertainty if I added those values together. Well, what I would need to do is I would need to add their absolute uncertainties. So my answer, for example, would be 5 plus 6, which is 11, plus or minus 2 millimeters, where I've added the absolute uncertainties. If the quantities are multiplied or divided, then we have to use the percentage uncertainties. So again, if I had taken two measurements of a measurement of the voltage and a measurement of current, and I was using that to work out the resistance, so the resistance is equal to voltage divided by current, there I would have to work out their percentage uncertainties and then add those because I would be doing a division. So whenever we're multiplying or dividing quantities, we need to add their percentage uncertainties. If we're adding or subtracting quantities, we need to add their absolute uncertainties. And then finally, if a quantity is squared, this is the same as multiplying. So in this case, the percentage uncertainty is added to itself. In other words, it's doubled. What I'd like you to do here is have a little bit of a practice working out percentage uncertainties and then working out how to add uncertainties together to get an overall uncertainty. So what we've got here is a table of results for an experiment that a student has done. So they've got 5 densities that they're measuring. They've got 2 regular blocks of material, length, width and depth are given in the table. They've got a cylinder of material, and then they've got some water that they measured using a measuring cylinder, and an irregular shape that they measure the volume of this using the displacement of water again. So in the first two, we've got length, width and depth. We need to use those to work out the volume. So we need to work out the combined uncertainties. We need to work out the percentage uncertainty, and we then need to work out the volume with its uncertainty. And then finally, we've got the mass, and we need to use the mass and the volume to work out the density. And we need to do that for all of these examples.